Good afternoon and welcome to the Computational Science Colloquium series. And today I have the pleasure to welcome Professor Pavel Popov from the Department of Aerospace Engineering, who works in combustion and gonna give a talk about preconditioning and Hessian in reactive flow applications.
Thank you very much for that. Hello everybody, it is my pleasure to be here. So today I'll give a talk on Hessian Preconditioning for adaptive tabulation for reactive flow applications. This is work that has been supported by NSF's division of combustion and fire systems. So what is the basic problem that we're interested in? We're interested in the basic setting is that we have some sort of a function that we need to evaluate as part of a combustion simulation. And we have a procedure for evaluating it, but the evaluation is itself costly. So here, for example, we have an example of a partially stirred reactor, which is igniting, and adapting the chemical composition in time is by far the most costly part of the simulation. Okay, so we have an established procedure to evaluate f of x, but the computational cost is high. And in that case, rather than evaluating f of x exactly down to machine precision, it may be advantageous to approximate f of x with some acceptable area, like 10 to the negative fourth, if that allows us to crank out these f of x evaluations much faster. So an example of this, and one of the classic cases in this field is the evolution of chemical compositions in reactive flow simulations. Reactive flow simulations usually means simulation of combustion. If you have a burner in an engine and you want to solve for its performance. Okay, so in general, in a detailed calculation of combustion, we would have a detailed chemical mechanism which prescribes which are the relevant species present in the current flame and which reactions govern them. So then we can apply the Arrhenius model for chemical kinetics, and that will prescribe the rate at which each reaction is progressing, using the well-known Arrhenius formula that the reaction rate is equal to a pre-exponential factor A that depends on concentrations times the exponent of activation temperature over universal gas constant times the temperature. So to give you a taste of what these chemical mechanisms look like, here is the one that we'll be using today. This is a 10-species chemical mechanism for hydrogen combustion. And basically, the reaction that we learn in high school physics, high school chemistry, is H2 plus O2 gives us H2O. That is a very simplified global reaction of basically what we end up with. In practice, we have all these intermediate species, and the overall flames progress. For the overall flames progress, it is important that we track most of them. Here, with the exception of argon, because I'm not going to put argon in the air. And these species evolved by these 24 reactions that are given here. So here we have the proposed reactions that are relevant for hydrogen combustion. So, for example, we have here two hydrogen radicals plus H2O gives us H2 plus H2O, and here we have the prescribed rate constants. So, the pre-exponential factor, the activation energy, and here we have a constant that modifies the pre-exponential factor by an exponent of temperature. So, in general, this gives us a very stiff ordinary differential equation, because essentially we have that the current rate of change of the chemical composition is a function of the chemical composition, but that function can have a very stiff Jacobian. So let's say, for example, that we have something like a constant pressure combustor. So then H can be the initial composition of temperature as well as the mass fractions of the important species. an initial time t. And then we can say, for example, that f is going to be the temperature and the mass fractions a time step later, at time t plus delta t. Okay, so we might say then in that case, f of x is simply a matter of integrating an ODE, but for computational combustion, that can be quite challenging because usually the ODE is quite stiff, even in this case for hydrogen combustion, and even more so for hydrocarbon combustion. So, for example, here in this simulation, I'm using a time step of 500 nanoseconds, which may sound like a very small time step, but that's still 50 times larger than the largest stable Euler time step would admit explicit Euler integration of this ODE given by f. So in order for this simulation on the right, every single advancement of a particle step, so 140 microseconds. And this should be giving you nightmares because remember, 140 microseconds doesn't sound like much, but in a combustion simulation, you are incurring that cost at every grid cell and at every time step. So if you have a nice large grid of 10 million grid cells and a time interval of 100,000 time steps, which can be quite standard for combustion, you may have even larger grids. Then multiply those 140 microseconds by what is going to be 10 to the 11. So obviously, this computational cost is going to add up significantly. In general, whenever you have a cell-wise, time step-wise operation like that, you usually want to make sure it's on the order of 1 microsecond. Okay, so we want to do this faster. So what are some options to do this species advancement faster? Well, the most classic approach is to use Cartesian tabulation. So the idea is, f of x is a known function, so we can evaluate on a set of discrete points, and then we can just interpolate between those discrete points. So in that case, Cartesian tabulation will discretize the domain of x on a Cartesian mesh. So for example, if you have okay,
Okay.
Okay. So the classical case of flame table, which most of the standard computational combustion code would use, is they would discretize the domain, chop it up in each direction on a Cartesian mesh. And then how well resolved is that Cartesian mesh is going to determine the evaluation error between the linear interpolation that you get from the table and the actual function. And that works quite well when the domain is low dimensional. So the classic case is a flame table that resolves the flame properties based on the values of mixture fraction and progress variable. And here we have an example of why in this particular flame this wouldn't work, because I'm plotting the concentration of hydrogen peroxide on a 3D plot versus the mixture fraction and versus the mass fraction of water, which can be thought of as an ersatz for the progress variable. So the fact that this isn't a well-defined function because there is a spread in these scallop points in the vertical direction means that in this particular case, the mass fraction of hydrogen peroxide is not a function of the mixture fraction and progress variable. Okay, so Cartesian tabulation works well when X is just two-dimensional, three-dimensional. Now, in that particular case, our domain is 11-dimensional. We have 10 different species composition as well as temperature. We could do some clever stuff and reduce it by a couple of dimensions using conservation principles. But even if it's 9-dimensional, there is no way to chop that up in 100 divisions in each dimension, because then you need 10 to the 18th evaluation. So for 11-dimensional domain, even just 10 divisions in each domain is going to be infeasible. We're up against the curse of dimensionality. Now, fortunately, however, there is another way to do a tabulation on a problem like this, because as we can see from this scatter plot of the particles in this stirred reactor, they do not span the entire domain, the entire realizable range of X. So, for example, there's no particles here, and there's no particles here. So, a lot of times we tend to think of the actual part of the domain of X that is being accessed is lying on a lower dimensional manifold that is embedded into the fully realizable domain. And this brings us to the method of in situ adaptive tabulation. So this is a method that has been developed by my dissertation advisor over the process, over the span of about 30 years, and today we'll improve it just slightly. But first, let's talk about in situ adaptive tabulation. So this was developed by Pavel Popov in 1997 for reaction steps, but it is applicable for pretty much any function, provided that the evaluation also gives you an evaluation of the Jacobian. So the way that ISAT works is that ISAT builds a table of ellipsoids on which you can evaluate the function. So an ISAT table spans covers the access part of the domain with ellipsoids of accuracy. So I'm going to shorten that to EOA, on which linearization of f of x about the center of that ellipsoid with a non-Jacobian gives us a good approximation. Okay, and then central to ISAT is that in the evaluation of f of x, we also need to get a Jacobian, and this is something that we very often get when we're solving stiff ODEs, because most stiff ODE solvers like Steve Olet, for example, also give us the option to solve with the Jacobian. Okay, so then how does ISAT work? Well, let's say that we have a new query. Let's say that our query is here. Well, if our query is here, the ellipsoid of accuracy of this point here. So basically, all that we're doing is we're evaluating the linearization. We have stored this value and we have stored the Jacobian here. So it is as simple as evaluating linearity. Okay, and in that case, we don't need a new evaluation of the costly function f of x. Okay, now another option could be that we are far away from the ellipsoid of accuracy, but still close enough that once we evaluate the function at this point, we see that it is not that far away from the linearization on the previous point. And in that case, we can draw the ellipsoid of accuracy, because now we have new information that tells us that the linearization is still good up to this point. Finally, we can perform an add, in which case the new point is quite far away from this ellipsoid, and the value of the function is nowhere near the linearization value. So just having solved the function already and calculated the Jacobian, we're just adding a new ellipsoid at the new point. So of these possibilities, the second one and the third one are the costly ones, because they involve us having to evaluate the costly function. But they also help us to increase the span of the set of ellipsoids. Okay, so now you may ask, okay, so how do we determine the nearest ellipsoid of accuracy? And the determination by spanning a binary search tree. So basically, what is happening is that each time we add a new ellipsoid, let's say that we add a new ellipsoid here. We are also going to create a cutting plane between these two ellipsoids, and we'll create a new fork in our binary search tree. So if we have gotten to this ellipsoid, we now check on which side we are of this cutting plane, and that tells us which path of the fork to take. Okay, so when a new query falls, where a new query falls relative to the cutting plane determines which path is taken on the binary search tree. And Isaac has proven to be quite efficient in reactive flow speedup. It is in fact a feature on some versions of ANSYS even. I'm not sure. I'm not sure if they still support it, but it has even been incorporated in commercial software. But one Achilles heel of ISAT is that it only works. It only gives us this wonderful speedup once the table has been built, meaning once we have sufficient ellipsoids that we cover pretty much any point that a new query can come from. But once the table is built, an ISAT primary retrieve can be as much as 1,000 times faster than a direct evaluation. And whether ISAT is successful or not is going to depend on the number of ellipsoids of accuracy needed to span the access part of the domain, because at the end of the day, our computer has limited memory, so there is going to be a hard cap on how many ellipsoids we can have, as well as if you need 10 more ellipsoids to build the table, that means that you need 10 more direct evaluation. So the cost of building the table itself is going to be much higher. So each ellipsoid of accuracy costs us slightly more than a full direct evaluation, and if there are too many, we're still going to incur a lot of cost in building the table. And if there are too many if there are more than we have memory for, the table will never be built. So then ISAT will start giving unexpected error magnitudes. Okay, so with this in mind, let's talk about growing these ellipsoids. So how does the Hessian come into play? Now, one thing that I tried to look up for this talk, but unfortunately the internet was not forthcoming, is that I distinctly remember this quote from one of my freshman books. And the quote is that everything is linear for as long as it is. You know, the idea is that a Taylor series expansion will always be a good in a certain radius about the center. So the idea of this entire book is to make this region as large as possible. And to do this, we'll focus on the Hessian of the function f of x. So we consider the Hessian as just the second derivative of f of x in all possible directions. It's going to be essentially a three-dimensional tensor. We have one order from f itself and two additional tensor orders from the double derivative. And by Taylor series expansion, we can show that the leading order term for the leading order error term between linearization at x naught and the actual value of function x is going to be 1/2 x minus x naught transpose times the Hessian times x minus x naught. So therefore, the error that we're going to get for this linearization is going to scale at the amplitude of the Hessian times x minus x naught. And this tells us that if we minimize the Hessian, we can get away with using larger ellipsoids. So we can span domain with a smaller number of them, hence less effort and less memory cost. So for such level of accuracy, a smaller Hessian will increase the size of IFET's ellipsoids of accuracy. So let's see what we can do about minimizing the Hessian. And the way we're going to minimize the Hessian is using basic fully connected neural network. We are going to train a dense fully connected neural network to output a function f hat whose Hessian is going to be close to that of f of x. Because then, by linearity, if we apply IFET to just the remainder between f of x and f hat of x, if the Hessian of f hat is close enough to the Hessian of f of x, then the Hessian of what IFET sees, f minus f hat, is going to be smaller, and therefore IFET is going to work with larger ellipsoids. Okay, and then having this neural network preconditioning and ISAT, they can join forces. ISAT can evaluate f of x minus f hat of x cheaply, and the network can evaluate f hat of x cheaply. Then and then we can just add them up, and we have a full evaluation of f of x. Okay, so now we ask, so in this Hessian approximation function f of x, how close are we aiming for? And the beautiful part is that we don't have to be anywhere near close in terms of convergence. So even if we manage to reduce the Hessian by a factor of, which nominally is a terrible error, it is 50%, but even if we manage to reduce the Hessian by a factor of 2, that will still increase significantly the volume of the ellipsoids that we can take in a large dimensional sample space. So even reducing the Hessian by a factor of 2 is still going to lead an ellipsoid of accuracy whose volume is 2 to the power of p over second power greater for a p-dimensional problem. So obviously, in our 11-dimensional problem, if indeed the manifold was 11-dimensional, even reducing the Hessian by a factor of 2 is going to give us ellipsoids with over 32 times the volume. Okay, so then how can we build this Hessian approximation? Well, the simplest thing is just the most basic thing that we can think about in neural networks. So just let's say that the function f hat of x is just a standard neural network approximation to the function f of x with a standard RMS loss function. Okay, and just for completeness, let's define the neural network. Even though I'm sure that pretty much everyone has seen one by now. Essentially, we start with the inputs of the entries of x. We can say that's the 0th layer. And the neural network will have several intermediate layers before the final layer that is the output layer. So each intermediate layer has the following form. The new x is going to be equal to the old x multiplied by a matrix of coefficients which we need to determine, plus an offset which we also need to determine, and that is going to be the argument of an activation function, which is usually preset. Okay, and the final layer will look exactly the same as the intermediate one, so we just will not use the activation function. We just have an affine linear transformation. Okay, and the activation function is going to be specified. We're going to test several options for activation functions. And then the process of training the neural network is the process of determining these coefficients, Aij and Bi. And for standard neural network with an RMS loss function, those are trained using something like a stochastic gradient descent or one of the many other neural network training algorithms, so as to minimize the RMS loss, which is essentially the mean L2 norm between f and the neural network approximation f hat on the discrete points where we're training. Now, one thing that we should note is that training a neural network is a stochastic process. So here we have the exact same neural network with the exact same hyperparameter, but with different random number seeds for the state of the neural network driver, which is going to be part of PyTorch. So it is important to keep in mind that we cannot just train the neural network once. We need to train it several times and then take the best result out of that. Okay, so let's say we're doing a standard neural network training. Well, in that case, essentially what we're doing is we are essentially what we're doing is we're trying to match the function f of x at discrete points. Now, this will only minimize the Hessian this will only match the Hessian of f of x indirectly, provided that we make sure that we aren't overfitting. There, marker. I was expecting on using the feature. Okay, so let's say that we're trying to match this function. And we are training on these discrete points. Okay, so if we have some approximation that matches these discrete points, we aren't explicitly matching the Hessian. If our network overfits, we can still match these discrete points, but have the network look like this, which is obviously not going to be good in terms of Hessian because the second derivative here is significantly different than the second derivative here. We will avoid this by making sure that we always have much fewer degrees of freedom in our neural network than we do in the training data that we're using it on. Okay, so to ensure that there is no possibility of overfitting, our network's degrees of freedom are going to be kept significantly lower than that of the training set. So here, our training set will have, it will basically be on 10,000 points. So depending on the test case, it will either be 40,000 points or 110,000 degrees of freedom. Whereas the network will always have 5 layers with 10 neurons each, which basically gives us each layer has about 100 degrees of freedom. So overall, the network itself will have less than 1,000 degrees of freedom. And here we do see this in action. So here I'm showing the test loss of our training process. So what it usually looks like for most neural networks is that the test loss is going to decrease up to a point, and then it will grow. It will start growing again, right? That is the point where the network starts overfitting. Here, because we have much fewer degrees of freedom, that is not going to happen. Okay, so that is one way to estimate the Hessian implicitly. But we can do even better than that. So as we shall see shortly, the implicit Hessian estimation already works quite well. But we are interested in squeezing out as much performance as we can from our limited degrees of freedom. So to this end, we're going to, and by the way, you folks may have noticed that I keep saying we. You know, it's just because I'm trained in the Eastern European model. So when I say we, I mean myself and the reader. I don't actually think that highly of myself as to use the royal we. So to this end, we're going to propose an original log function, which is going to be based on a remainder from linear fits. What do we mean by this? Well, first of all, what we're going to do is we're going to break up the training set on a collection of k-means clusters. So let's define the cluster IXP to be the set of a number of p points, you know, something like 20, for example, near a given point x, including it, and that set of points is going to be chosen using k-means clustering. So here we have an illustration of k-means clustering. kindly provided by the KOX project. Okay, so then let's say that on each cluster we let's pointer. So let's say that on each cluster we perform a linear fit both to the actual training data as well as to the current state of our new neural net. Let's say that FLF of X is a least squares linear fit to F on the points of the current cluster. And we're going to do the same thing for the neural network function. We're going to define the new loss as the RMS of F minus its linear fit minus the neural network function minus its linear fit. So then, what does that do? Well, F minus its linear fit essentially gives us this point, and this point. The neural network function minus its linear fit is going to give us this point, and this point. So this means that even though the neural network function may not be anywhere near close to F, may have a different value and different slope, we are still extracting essentially the second order differences that form discretization of the Hessian. So in that sense, we can say that this loss is an explicit Hessian estimation because it disregards any zero and first moment differences between the two functions. Okay, so we can say that for one of K-means clusters, minimizing this epsilon LF is going to minimize the Hessian explicitly because by the mean value theorem, this approximates the Hessian at the center mass of that cluster, and this approximates its Hessian at the center mass of that cluster. So minimizing their difference means that we're matching the Hessian. Okay, and both the new loss and the K-means clustering algorithm are implemented in PyTorch. The new loss is original. The K-means clustering algorithm is well established. I just it is courtesy of the KOX project, and the new loss may look complicated, but it is literally just these 5 lines. We're taking a least squares, we're subtracting the least squares, we're taking a least squares for retarding data, we're subtracting the least squares, and then we're taking the RMS mean of that. Okay, and then for both kinds of losses, we're using the ADGRAD optimizer just to define the training process. For the RMS loss, we're using a learning rate of 0.05 with a 0.8 decay every 1,000 epochs. So every 1,000 epochs, we are decreasing the learning rate by 20%, and we can actually see that. We can actually see that here when we have the loss for the RMS loss, because this oscillation is basically due to an excessive learning rate. So as we decrease the learning rate, these oscillations decrease, and we get attracted to a local minimum. Okay, and then for the explicit Hessian loss, we use half of that learning rate without the decay. And here we're using ADGRAD, but this other optimizers were also considered, such as RMS Prop, Adam, and FGD. Those are the classic ones in machine learning. And ADGRAD just happens to provide the fastest neural network training convergence. And as I said, as the training process is stochastic, each network is trained 5 times, and we pick the case that gives us the lowest loss for comparison. So here, for example, we have the training process with the new loss, where for the first 6,000 epochs, we are starting with the standard RMS loss, and then we are switching to the new loss. So there's going to be a spike in loss at the switchover, but then the new loss keeps decreasing. Whereas on the previous slide, you saw that the RMS loss plateaus out much earlier. Okay, and we have defined how we set up and train our neural network. So let's talk a little bit about the activation functions. Now, for this particular application, the choice of activation functions is important because we want to be getting not just a function value from our neural network. We want to get a Hessian. So first of all, we want to make sure that our activation functions are at least twice continuously differentiable. So we want functions that can be evaluated cheaply. We also want functions which allow the training process to converge to a good solution. So here, we'll test pretty much all of the classic C infinity activation functions used in machine learning, as well as a newly proposed function, which unfortunately I had very high hope for, but it turned out not to perform. Okay, so we have Mish. It looks like this, and here they're all plotted. So Mish is this black one, and Mish turns out to be the one that performs best. Then we have the Gaussian error linear unit. That's going to be this blue one. We have the sigmoid linear unit. We have the soft plus. We have the sigmoid, and then finally we have my baby, which doesn't turn out to work that well. Now, the reason why I have proved that one is because in general, evaluating an exponential function such as this one and this one is somewhat more costly than evaluating square roots. So I was hoping that that will give us a faster evaluation, but as it happens, the computational cost of the function itself is not. Okay, so before we move on to the full eyesight case, we are going to introduce an analytic test case. And here I'm showing you a two-dimensional cross-section of that. So we're going to have a four-dimensional domain. X, Y, Z, and T are within a 0 to 1 four-dimensional cube, and the function is just going to be an error function with respect to the radius based on X, Y, Z, and T. But we're making sure that this error function has a very high gradient. So we're multiplying it by 20, so that in the middle of this domain, the error function quickly jumps from 0 to 1. And this is done to model some of the issues that we're getting in computational combustion. That as our temperature increases, our reaction rate quickly jumps from pretty much nothing to a very high value. Okay, so for this analytic test case, what we're going to do is we're going to train on 10,000 sample points, and if we use the K-means clustering loss, we're going to use 500 clusters with 20 points each. And then because here we know the analytic function, what this test case allows us is to calculate exactly how well we are approximating the Hessian. So that is useful when we're tuning the hyperparameters. And it was found during the optimization of this test case that for this particular problem, we get the optimal performance when both x and f of x are scaled in such a way that both f of x is on the order of 1, and the gradients of f of x are on the order of 1. So here, you may be wondering if my domain is from 0 to 1, why is this range from 0 to 20? it's because I have scaled my my input arguments in such a way that with respect to them we have gradients of order about 1. Okay, and particularly this is also the best practice for ISAT. Okay, so for this test case, the object is to tune the hyperparameters, such as the number of layers, the number of neurons, the learning rate, etc., in such a way that we can minimize the RMS of difference between the actual Hessian and the neural network Hessian divided by the actual Hessian. So here we have for z and t is equal to 0, we have a plot of the square of the actual Hessian, and we have a plot of the square of the difference between the actual Hessian and the neural network Hessian. So as you can see, the difference for this optimal trained network is significantly less than the actual Hessian, with the exception of here. And also here we have the actual difference between the function and the explicit Hessian neural network function. So one thing that we can notice that the actual function differences are quite large, but we should note that most of that is essentially a linear function that does not affect the Hessian whatsoever. Okay, so here we show for z and t typical results for the difference between the true and the Hessian and the neural network function, and as well we show the amplitude square of the Hessian and the amplitude square of the difference between the true Hessian and the neural network Hessian. So the neural network is performing quite well, and it's minimizing the Hessian as it should. Now here, as I said, we should notice that the function difference is on the order of 1 for the newly proposed loss, but since the majority of this variation is linear, it does not matter. We know that the Hessian difference is well under the original Hessian amplitudes, but we do know something that is thought for further research. That here, where the actual Hessian is identically 0, we are getting some non-zero variance of the Hessian difference. So this is basically just from spurious curvature in the neural network. This comes from here. Okay, so in general, it was found during the training process that the Hessian estimation exhibits larger errors near the boundary of the domain, and one possible reason for that is that near the boundary of the domain, we only have training points on one side of the boundary. So then the effective stencil for approximating the Hessian is not centered, but rather it is offset. Okay, so now let's talk about how these activation functions perform. And in terms of computational cost, the activation functions do not actually make that much of a difference. So here on the top, I'm showing you the cost of evaluating this neural network per grid cell per time step. So remember, the cost of the actual function was 142 microseconds. The cost of evaluating the neural network for pretty much all hits is less than 1 microsecond. So the evaluation cost of the preconditioner is about 1/1000 of a direct evaluation of the function for a network with, for our hydrogen case, which has 11 inputs and outputs. Now, the activation function itself does not affect that much of the cost of an evaluation. It happens that most of this cost comes from the matrix multiplications rather than evaluating the.
Don't change that slide because I have a fondness for Fortran 90, so I want to take a picture.
Fortran 90 is most excellent. In fact, this is a combination of Fortran 90 and C++, because essentially I'm using 2 libraries, one of which was written in Fortran 90, that's ISAT, and one of which was written in C++, that's Cantera, that does all the chemistry. So I had to do some interfacing between the languages.
The Fortran rule.
and it is extremely fast. And in fact, I'm showing that here because here the cost of evaluating pretty much all the activation functions is basically zero. This cost is mostly just a match for multiplication. But when training the network, the value activation function is in fact 20% costlier in the training process. I think just because Python isn't anywhere near as well optimized as Fortran 9. It is just not that fast. Now, the activation function does, however, have a major effect on the Hessian accuracy. Here we have the norm of the Hessian difference divided by the norm of the true Hessian, the average of that. And we can see that depending on which activation function we pick. So the blue ones are the new loss, and the orange ones are the basic implicit loss. Depending on which one of those we pick, we get one of the different results. And here we want to have this norm be as low as possible, because that means we're reducing the Hessian. So the optimal case is going to be mesh with explicit Hessian. Next question.
Do you explicitly evaluate the activation functions while training, or I mean, you could tabulate them, right? Interpolation.
Honestly, I'm not that familiar with the inner workings of PyTorch to answer that question, but I do believe that PyTorch evaluates them explicitly. And in Fortran, I definitely also evaluate them explicitly, but Fortran the new Intel compilers for Fortran are so quick that it really doesn't matter. You can hardly see it. Okay, we get the best case approximation when we use the mesh activation and the Galo activation. And for those two choices, the new loss based on that explicitly approximates the Hessian further reduces the Hessian norm by about 40%. And here, soft loss is all over the place. In fact, it diverges during training. So this particular this particular activation is not even valid, but we tested it for completeness sake. Okay, and therefore, since mesh is both faster for training and on the PyTorch side of things, and it is slightly more accurate than Gelu. For all the rest of the test, we are proceeding with just mesh for the Hessian preconditioning. Okay, so now let me, because I see that I'm running low on time, let me quickly define the reactive flow test case. So our reactive flow test case is going to be a partially stirred reactor, and a partially stirred reactor is basically a zero-dimensional model of combustion. We have a collection of points, and periodically we're adding new fuel particles or new oxidizer particle. Periodically we're taking away existing particles, and then as the simulation progresses, we are evolving each particle's composition, and periodically we're mixing particles with each other. So instead of evolving the chemical composition via PD solution, they're evolved out of 7 discrete points. So for each time step delta T, we do a reaction where we are solving this costly function, or we're approximating it. We do mixing. We pick 2 particles at random, and we take them some part of the way to their mass weighted mean, and we do inflow and outflow. Some probability we're just taking a particle and we're replacing it with a brand new particle of either fuel and oxidizer. And then what is the mixture fraction of the overall reactor? It's going to depend on the probability that we pick fuel or that we pick oxidizer for the new particle. So here we have this in action. So here I'm showing the temperature of this partially stirred reactor. What is the mixture fraction? And the mixture fraction is basically the ratio of how much of a particle comes from fuel and how much it comes from oxidizer. So here, this mixture fraction of 0 is stuff coming from the oxidizer, and this mixture fraction towards 1 is stuff coming from the fuel. Now for hydrogen, the stoichiometric mixture fraction is about here, 0.028. So in this particular case, we are our mixture fraction is our mean mixture fraction is about 0.1, so we are quite rich. We still have a large strong flame because hydrogen is hydrogen, and it burns really well. And here we see the evolution of OH radicals, and note that this is on log flow. So here, while the reactor is igniting, we have exponential growth of the OH radicals until they reach their steady state level. Okay, and the reaction conditions, the fuel still is pure hydrogen at 1050 kelvins, the oxidizer is pure air at 1050 kelvins. This is significantly above the ignition temperature, so this reactor proceeds quite quickly. Global mixture fraction is 0.1. The pressure is kept constant at 1 atmosphere, and the reactor consists of 2500 particles, which are evolved for 4,000 time step for an overall accumulation time of 2 milliseconds, which is still quite sufficient for this reactor to achieve steady state because the reactions happen quickly. Okay, and as I said, we're using this partially stirred reactor as a model for the kind of chemistry that we get in a full, something like a direct numerical simulation, computational combustion simulation. So, how well does a partially stirred reactor generalize? Well, ideally, it should give us the same distribution of compositions that a three-dimensional simulation would. Now, in practice, the partial stirred reactor as a test case is going to be milder than a full simulation in some respects and more challenging in other respects. It's going to be milder because there is no differential mixing, at least the way I've defined it here. So, two particles, each of their species are going to mix at the same rate. So we are, for example, replicating something like a hydrogen diffusing more quickly in hydrogen combustion. But on the other hand, it is also more challenging because we pick any two random particles to mix, which is a larger range of possibilities than what we have in a combustion simulation, because in a combustion simulation, we get mixing from diffusion. So therefore, the only compositions that are going to mix are compositions that are close in space, and therefore compositions that are also close in composition space. Okay, so let's finally get to the good stuff, and let's see how our Hessian preconditioning tie set performs. So here we have some analytic results. So first of all, we're going to test on the four-dimensional analytic test case. And we're going to test each of the three options. We can either do just standalone ISET, which is our baseline. We have to do better than standalone ISET. ISET with implicit Hessian preconditioning, that's the basic neural network, just a standard RMS loss, and we can do ISET with explicit Hessian preconditioning. And in ISET, we can vary the accuracy that we want to achieve by specifying a parameter, which is a user-specified error tolerance that ISET is trying to get. So here in these simulations, the different abscissa values are. No, I am still speaking English. The different abscissa values are going to be different values that we have specified for the user-specified error tolerance. So here the simulation that we want to be rough, finer, and even finer. And here on the top we have the overall error that ISET achieves. On the bottom, we have the number of ellipses that have been added to the ISET table. So in both cases, we want to be as low as possible. Okay, and in this particular case, because this is a simple test case, it is a four-dimensional analytic function, we allocate very little memory for the ISET table. So our ISET table can only have as much as about 8,000 ellipsoids. So the table is going to run out of space at a fairly high error tolerance. If we want to decrease the error tolerance, we can just allocate more space to the ISET table. And a successful ISET run should achieve the desired error tolerance, meaning that this symbol here should be below this green line. So this green line is the line that demarcates the actual error being less than the user-specified tolerance, with as few as possible. So we want to make sure that this is low. And for this case, and for this table size, the standalone ISAT achieves the specified error tolerance only for the larger user-specified error level. Beyond that, ISAT basically standalone ISAT basically runs out of room, and the accuracy in fact decreases. Whereas our new Hessian preconditioned ISATs do much better. They achieve the error tolerance for the implicit case for the first 3 user-specified errors, and for the explicit case for the first 4. So, in contrast, explicit Hessian and ISAT achieves the first 3 target accuracies, and the implicit, sorry, the other way around. Explicit Hessian and ISAT achieves the first 4, and the implicit Hessian and ISAT achieves the first 3. And we can see that they achieve that with needing much fewer ellipsoids. So here we have, and note, this is a log plot. It is a semi-log plot. So here we have something like 140 ellipsoids. Here we have 9. Here we have 3. So using preconditioning, we can achieve the same accuracy with much fewer ellipsoids. Here we have finally the full test case using hydrogen combustion. And as I said, how much memory we allocate for the table is important. So I'm going to run these test cases both for a 50 megabyte table and for a 500 megabyte table. So for fixed table size, as we reduce the allowable error, we increase the number of ellipsoids that are needed to span the space of queries. And when this number of ellipsoids strikes above what is allowed by memory, so when we hit this part is when you see we start our accuracy starts decreasing instead of increasing because we can no longer span the full domain with our table. And of course, adds going to have computational cost, so the fewer the better. Okay, so in particular, each ad costs about 200 microseconds, whereas each direct evaluation costs about just one microseconds. So here we know that implicit preconditioning and ISAT reduces the number of ads needed by over 1 order of magnitude, and explicit preconditioning further improves on that reduction. So that's those are the yellow lines here. And finally, I'm going to briefly skim over the larger table size. So here we see the same results, but because we're allocating more room for our table, we can actually achieve for all 3 types of ISAT, we can achieve the error that we desire. But of course, standalone ISAT still requires the largest number of ellipsoids in order to achieve that error. So once again, we see significant reduction in the number of ads when preconditioning is used. Okay, so conclusions and future work. So we have developed a new method for improving on the performance of linear tabulation. And this could be applied not just to ISAT, but pretty much any linear tabulation algorithm, but here we tested it on ISAT. For zero-dimensional hydrogen combustion case, the implicit Hessian preconditioning reduces the number of ellipsoids by more than a factor of 10. And the newly developed explicit log function further improves on that. The added cost of the neural preconditioner is negligible. In particular, for this incarnation of the network that uses a low number of neurons. And the image activation function seems to perform best at estimating the Hessian. So for future work, we'll test this approach with hydrocarbon combustion. We'll integrate it into a 3-dimensional turbulent flow simulation, and we'll look into possible improvements into ISAT itself, because while performing these tests, I noticed that the ISAT itself doesn't scale quite as I would expect it. And with this, I conclude. Any questions?